So welcome back to this presentation on shift registers. So in our previous discussion we have already seen how exactly a shift register works. Conventional shift register, uh, basically what exactly are the commands required, that is to load, then shift, the second one, and the third one happens to be reset. So these three commands are required in our shift register operation, and we have seen one example with the help of 4-bit shifts, right? How exactly a typical shift register operates. And later probably we were looking at this particular example wherein you consider the case of designing rejection mechanism, that is so rejection mechanism of say uh, faulty item, something like this, right? So rejection mechanism of some faulty item. Now if you look at this diagram, so I think in the previous class also we have seen it. So now this is the conveyor belt over which let us say some items keep moving for the packaging purpose or something like that. So as long as the items are healthy, so they will be deflected in this direction for the purpose of packaging. But if the items are found to be unhealthy or faulty, so you may have your own mechanism to identify that. I am not discussing about how would you identify a faulty item here, right? So some of the examples also I have given. If the liquid level is not up to the mark, okay, the desired mark, or if there is a change in the color of the liquid, right? So, or if there is a change in the pattern of the box, or if the bottle is uncapped, right? Capping mechanism hasn't worked. For all these kind of applications, there will be some kind of sensors which are deployed to identify those things. And let us assume that some mechanism, some kind of sensors are at place in order to identify the faulty items. So once the faulty item is identified, so instead of immediately deflecting them to uh, some bin or something like that, right? So you would wait till that particular item comes to a particular place, right, where you will either deflect it this way, or you would continue it to move in this direction. As long as the item is faulty, you would deflect it this way, and if the item is healthy, it would go in the appropriate direction. So in order to do this, we need to design a mechanism using the shift registers, right? So here when we speak about using the shift registers, first you should try to understand what exactly are your requirements. So now you may need some input to identify the element which are moving here. So element means it could be healthy element or faulty element. Now if you look at this diagram, there are totally 8 elements which are moving along this conveyor belt, out of which now as of now you see there are 2 faulty items, but in fact it is virtually one only, because I am representing the condition this item coming to this particular place, right? So 1 2 3 4. So in the fifth place this needs to be deflected. So there may be n number of such items, right? So when there are n number of items, you should see to it that the healthy items are moving in one direction, the faulty items are moving in another direction. So having said that, when you want to write the ladder diagram, or when you want to write the program, so there should be the mechanisms to identify the elements, right? All the elements irrespective of whether they are healthy or faulty, and there should be mechanism to identify the faulty element. So there should be at least two switches required in this particular context to identify the things. Then the next thing is that, okay, so once this particular item comes to this particular position on the conveyor belt, right? So you should have some kind of mechanism, which I have already told you there here. Okay, so this mechanism, whatever is there here, okay, so this mechanism is an output device or something like that, right, which is called as deflecting mechanism, right? So you may have some kind of mechanical action taking place there, so this deflecting mechanism should come into picture. So at least two inputs and one output is required here, along with the internal relays which are required for loading, shifting and resetting operation, right? So accordingly we should be able to draw the ladder diagram here. I would continue from here. So now my rung begins somewhere here. These are the power rails. So let me first consider one input. This is my, say, X400 or something like that, and this is going to, say, load your input. Okay, so that means how many items are coming on these things, right, on the conveyor belt. So that is indicated by this, right? So now here let me write this as say X 400, or yeah, X400 I can write, then followed by this I would write as M140, and here this is basically out. Let me take it like this way, right? M140 internal relay, out, as you know, right? So it is for the purpose of loading. Here you have already seen it, right, for the purpose of loading. So now when I say it like this, this is basically to indicate the faulty item, right? So whenever you have this, so now your shift register, after having identified the faulty item, it will be loaded with 1. So now the next task is to have it shifted 4 times to the right, and after the 4th time you will have to activate the output device, which is Y430, and accordingly let us try to draw a portion of your ladder diagram. So now let me take up the next input, and this goes to one more output, and this input, let me take it as X401. I would explain all these things. X401, and here this is again M140 with SFT. So this has to shift the output, M140 with shifting, right? So now let me have one more rung here, because this rung is required to reset M140. Somewhere here I would write it as something like this. So this I will take as X 401, 402. Let me take it as X402, and here again this will be M140 and RST. I will take it here, M40 and RST. This is shift. Now yeah, so after this maybe in our fourth iteration, right? When I have got it a fourth time, right? When the shift is done fourth time, when the loading is done for the fourth time, like what I have shown you here. So this one moves here, this one moves here, this one moves here, this one moves here. Maybe this could be 0 or 1 depending upon what exactly is coming from here, right? Let us not worry about that for the time being. So once you get the fourth moment, that when this becomes 1 here, so you should be able to make your put high, y430 high. So but before that, you may require some mechanism for resetting purpose. Resetting purpose in the sense, you can see here, see, once the first item is first faulty item comes here, this comes here now, okay. So this is deflected, okay. So now the faulty will move in this direction, but the very next item could be a healthy item, okay. So as long as it is healthy item, move in this direction, right? After this is deflected, immediately it should make sure that it should go back to the original direction, right? However, if there is one more faulty item coming, then definitely it will see to it that it will again deflect it. That all depends upon what comes here, that is whether a 1 comes or 0, that will decide whether you have to move in this direction or you have to deflect it in this direction. As long as it is 1, it should deflect. As long as it is 0, it shouldn't deflect. So that's what is the requirement. So for that, you must a rejection mechanism also here, right? So your output, say y430, it is activated, right? So once deflection takes place, right? And it should at the same time also see to it that no healthy item should be rejected, which will immediately follow the item which has already been rejected, right? Or yeah, it is deflected. So now for that particular purpose, you should have some more things here in between. Let me just draw that and I will explain. So now let me take one more input as say x403 here, followed by I would have the contacts of your relay M144, and you have one more internal relay here, right? So now this internal relay contact would come here. So this I would write what exactly it is. I first write it as X403, 402 is already taken here, X403 followed by M144. You know what exactly is M144? This is the fourth bit of your relay which is responsible for the deflection, right? And I am using one interlay here, M100, and again this will be the same M100 here. So now please see here, after this what I would do here is I would use the final rung which is required for me to have the deflection of 40 items. Before that, resetting that output, for the purpose of resetting that output, I would have the M, write this as Y430 here, this is Y430, and this one is my M100, and here I would have M144, and this here would take me to the end rung. This is my end rung, And now, yeah, let us see. And here I should have one more.
Whenever now this x identify, so let me write, yeah, x 400 is used to identify the faulty item. This is very important for you to note down, right? So now every time a faulty item is identified, as we have already seen earlier in this uh, conveyor, right? So you would get input to your X400. This is the first point to be noted, right? Every time the faulty item is identified, so an input you will get for X400. Now when you have X400 activated, you would get one here, because that will activate your input the internal relay M140 with this out. So as long as there is a pulse here, so you will have one here, right? So this is one thing. Then the second rung, when you come to the second rung, you can see here, and this is this will be latched now because your M1 for here. So now when you come to the second rung from the first rung, what exactly happens is X401 is used for the purpose of shifting, as you can see here, right? X401 here in this case, your X401, okay, is used to identify the items, right? All. I can write this as all, because whether it is faulty or healthy, all the items are going to be identified by this X401, right? So that means when the next pulse comes, when the next item comes here, when the next item comes, this keeps moving, right? So when the first item comes, both X400 as well as X401 will get activated. One second, I'll just, okay. So when the first pulse comes, X400 as well as X401 get activated. But when the second pulse comes, your photo sensor is designed in such a way that only 401 is activated. Now depending upon how many number of pulses or how many number of items move on the conveyor belt, irrespective of whether it is faulty or healthy, your X401 will give the output. So since that output is connected to M140, which is shifting, so your shift, a 4-bit shift register, whatever the initial one was here, now it gets shifted here, right? Next it gets shifted here. Now whether the next one will be 0 or 1, that all depends upon whether your X400 is only activated or your X400 is not activated, depending upon it is a faulty item or healthy item, right? So accordingly it gets shifted here. It could be 1000 also, it could be, so next it could be 100 also, depending upon one more faulty item. So next could be 0110, something like that. It keeps moving, right? In the fourth iteration, first bit will come here, indicating that it is a faulty item. So therefore your second rung here basically indicates passage of the item irrespective of whether it is faulty or healthy, right? So now your X402 is basically a reset mechanism here, right? So now please check how many times your X402 is appearing here in this diagram. It appears only once. So whenever you want to have the reset, then only you would have the input from your X402. Otherwise your X402 doesn't participate in this shift register action. Okay, so then the next instruction you can see here, you have X403 again latching with M100, then your M144, this is very important now, M144 and M100 again. So this particular rung X403, M100, M144 and M100. What exactly this particular rung does here, right? So now when the one reaches internal relay M144, the this one, okay, so one is by this, or it activates the output. So now I am coming here, and this action would not happen until I come to this, because see this M144 is closed, okay, only after the fourth operation takes place or the fourth item has moved. Okay, so now when this is closed, when M144 is closed, you would have, you can see here Y getting activated, because this one, that is M100, is already a normally closed switch. Okay, so now once your Y430 is activated by means of some deflection mechanism, right, Y430, and you are deflect the conveyor to put your faulty item here, and once the faulty item is put, immediately after that you should have the resetting of this rejection mechanism. So resetting of this rejecting mechanism takes place by virtue of the input X403. You can see here the input X403, which is again latched by M100, and this M100
take into account all the kind of actions that are supposed to take place in such kind of mechanism. This in general you can consider it as fault, or deflecting mechanism in order to identify the faulty item. Whether it is only after the fourth, iteration, or after the second iteration, after the eighth iteration, that all depends upon what kind of shifts you are using here. Whether you are using a 4-bit shift register or 8-bit shift register, that will decide, right? Or that will even give sufficient time for your deflecting mechanisms to get activated and deactivated, because they are basically your mechanical devices, right? So now this is one such application wherein you can see how exactly typical deflecting mechanism works here, right? And you can even write the instructions for this, right? Instructions are quite simple here. You start from your LD X400, then out M 140, right? So then again out, or okay, before that you have this M140 as the latch here. So if you want, we will write the, the instructions. So Let me, yeah.
But what really happens is you should be able to write the programs with the optimum number of rungs in the ladder diagram. That's what I have told you in the earlier classes also, right? So now, before we go into some of the practical examples, we need to look into some of the aspects related to the data handling in PLC. Data handling in PLC, right? So far, what we have seen is entirely different, right? So we will either operate based on the input from a switch, right? Based on the input from an internal relay, or based on the action of a timer, right? Based on the action of the counter, based on the action of the shift register, so on and so forth, right? In all these cases, your operation is dependent on the bit operation. PLC operation is based on the bit operation, right? So bit operation in the sense, so now you have got a switch, say X400, so it is a switch, right? So sometimes it may be open, sometimes it may be closed. So once it is closed, some act. Once it is open, some other action you will initiate, right? So you have got a for example, right? So once, say, your K is 5, the timer setting is 5. After 5 seconds, you initiate some operation, right? Up to 5 seconds, you do not initiate some operation, right? In your counters, right? When your counter reaches the terminal count, you will reaching the terminal count means what? It is again basically operation, right? It starts counting from 0, 1, 2, 3, 4, 5, something like that, right? It is one bit operation. Shift register also is a bit operation. But when I speak a byte, okay, so you load some preset value, for example, okay, so now I have loaded a preset value in my counter or something like that. So that may be an 8-bit data, that may be a 16-bit data, that may be a 32-bit data, depending upon what exactly is required, right? So then you measure something in the industrial process, right? So for example, I want to have the temperature setting. I want to have the temperature setting. So my temperature is for say 35 degree centigrade, right? So I use some sensors here, temperature sensors.
once the measured value in the temperature sensor becomes equal or greater than this 35, I must activate some output or some solenoid, some lamp or something like that, some output device, right? So when I speak about 35 degrees centigrade, it is no longer a bit. This is one important point to be noted. It is going to be a byte, right? Or it is generally called as word in your microcontroller scenario. It could be an 8-bit word, it could be a 16-bit word, or it could be 32-bit word, 64-bit word, depending upon a type of the processor which you are using there, right? So whenever you deal with the words in your PLC, it is also possible for you to deal with the words in the PLC, and whenever you want to deal with the words in the PLC, then you need to have some of the data handling operations, right? Or the data handling uh, procedure, right? So that is also permitted in your, and whenever I want to handle the data in a PLC from bits, okay, I would move to registers. Even in the shift registers also we have, though it is called as the register, we have handled the bits only there, bits getting shifted, right? But using the register as a whole, could it be 8-bit or 16-bit or 32-bit? Then if you use all the bits simultaneously, right, then we go with data handling. We go with data handling. So there are certain important instructions, there are certain important aspects related to the data handling even in your PLC also, and that also becomes a part of your PLC programming. How would you handle the data whenever your analog sensors measure some data, right? How would you convert them into your digital values? How do you place them in the bitwise manner? Will it remain an 8-bit data? Will it remain a 16-bit data, or 32-bit data, or 64-bit data? And whether a type of the PLC that you are using there, right, is it possible for PLC to accommodate that data if it is a 32-bit or 16-bit, right? So all those aspects are to be seen, and accordingly you have the different data handling instructions in your PLC. And basically when we speak about the data handling, right, so we represent all these decimal numbers in the form of BCDs. All of you know what exactly we mean by binary coded decimal. Every number is given a binary code. Now for example, if you have a, okay, so most of you must have seen this in your suitcases and all, right? So you can rotate it, right? It will become 2 3 something like that, right? So you can set up something, so some for setting purpose in suitcases and all, a 3-digit number if you keep, it gets locked. Unless you bring it to that particular number, it will not be able to open it. That kind of things you must have seen, right? So now each number here is represented by a binary code, 0 0 1 0 if it is 2, right? If it is maybe you have thumb wheel switches here, right? One is 0, another is, let us say that it is, okay, so 0 0 0 0, then 8 is 1 0 0 1, then 0 0 1 0. So now here that is 082 basically, or 082 is represented by this particular number, right? So now this 082 is basically an analog data for me, right? And as long as I measure a temperature 35 degrees centigrade, I should be able to represent this 35 degrees centigrade, and accordingly this 35 degrees centigrade should be compared with some preset number to identify whether it is equal to that or greater than that or less than that. So all those things, right? So the basic representation of a decimal number will be in the form of binary coded decimal, like any other kind of digital devices. But even though you represent them in the binary coded decimal, you must have some instructions to handle this data, right? So what are the data handling instructions? Could it be the data movement instructions, something like this? Data movement from one point to another point, what you can call it as source to destination, right? So the data movement could be from source to destination. Then you may have some data manipulation instructions, right? So manipulation in the sense data maybe comparison, right? The data comparison instructions. Then you will have some arithmetic instructions, right? So all these type, whether it is a movement from source to destination, whether it is to compare with some standard value or preset value, or the value which is kept as the reference, right? Or could it be the arithmetic instruction? Arithmetic instruction means your simple addition, subtraction, division and multiplication. So these type of instructions we have not come across so far, right? So we have seen only the ladder diagram, wherein some switches are there, some actuators are there, and some kind of internal relays or timers or counters or shift registers are there, and subsequently there are some output devices. But when you deal with some analog data, when you deal with some analog values as the variables, right, in your PLC systems, how do you handle them? Whether the PLC permits the handling of these data which are analog in nature. If so, what are the different types of the data movement instructions, and in what type of situations we generally come across these data movement instructions? In some simple examples and all we will have to see, right? So probably in our next presentation we will look into some of the data movement instructions, followed by your important controllers like your PI controllers, PID controllers, how the PID controllers are important and relevant in our PLC environment, because the PLCs are basically deployed for the purpose in your industrial process control, where your P or PI or PID controllers are very much essential, right? So let us stop here, and in our next presentation we will see something about the data movement instructions or comparison instructions, arithmetic instructions, some of these examples, followed by the PLC controllers, right, or the closed loop control in the PLC systems, right? So I will stop here now. We will meet again in our next presentation.